The topic of this lecture is paging. Paging splits up the address space into fixed-sized unit called a page. We've covered the segmentation. Segmentation is various sized logical segments, such as code, stack, and heap. And segment has starting address, an end address, and size. This is an attribute of the segmentation. With paging, physical memory is split into some number of pages called a page frame. And page table is per process data structure. It is needed to translate the virtual address to physical address space. The advantage of using paging is flexibility. It supports the abstraction of address space effectively, and it doesn't have to make any assumption about how heap and stack grow and are used. And it is very simple. It's very easy to manage the free space because the page in the address space and the page frames are the same size. So it is easy to allocate and keep a free list. Let's consider an example. We have 128 byte physical memory with 16 bytes page frame. 16 byte page frame, and there is 128 byte physical memory. So there are 8 page frames in the physical address space. And let's assume that a process address space consists of 64 byte. So it corresponds to 4 16 byte pages. So there are pages of 0, 1, 2, and 3. So this is virtual address space of the process. And when we load this virtual address space into memory, there is a page table, and each of these pages can be freely located to any of the page frames. In this example, page 3 is loaded on the page frame number 2. Page 0 is loaded onto page frame number 3. And page 2 of the address space is loaded onto page frame number 5. And page 1 of the address space is loaded to page frame number 7. So, because there is a discrepancy between virtual page and the physical frame which the virtual page is located, we need a mapping or a translation layer. So there are 2 components in the virtual address. First one is virtual page number, and then offset within the page. Let's consider this 6-bit address space. Because we have 4 virtual pages in each virtual address space, we need 2 bits to represent virtual page number. So we need 2 bits, and then there are 4 bits offset. So virtual address 21 in 64 byte address space corresponds to as follows. So 21 in decimal number corresponds to 01, 01, and 01. And first 2-bit, the leftmost 2-bit corresponds to the virtual page number, and the rightmost 4 bits represents an offset. So in this address translation, we have virtual address 21 in 64 byte address space. So we need a mapping table that maps a given page number to the physical frame number. That's what is page table for. Then the next question is, where are page table stores? There exist hundreds of processes, and each process has its own address table. So each process has its own page table. So the total size of page tables can get very large. Let's consider 32-bit address space with 4 kilobyte page. Then because we have 4 kilobyte page, this is 4096 byte. So it corresponds to 2 to the 12 byte. So we need 12 bits for offset, and then out of 32 bit, if we allocate 12 bits for page offset, then they'll have 20 bits. So there exist 2 to the 20 virtual pages in its address space. So 2 to the 20 virtual pages, and let's assume that each page table entry is 4 bytes large. And then a single page table can be as large as 4 megabyte. If there are 100 such processes, then total page table sizes sums up to 4 megabytes times the number of processes in the system. It corresponds to 400 megabyte. Let's get back to our original example. There are 8 page frames, and then there are 4 pages loaded into page frame. Page 3 is loaded on the page frame 2, and page frame 3 contains page 0, and frame number 5 contains page 2, and page 7 contains page number 1. So this is an example. And let's look at the format of each page table. Page table data structure that is used to map the virtual address to the physical address. So the simplest form of page table is a linear page table, an array. So OS indexes the array by virtual page number and then look up the page table entry. Let's look at the entry details of the entry. Page table entry contains page table is indexed by virtual page number, and then it contains physical page number, physical frame number, and there is flags. And these flags contain various information about the associated pages. First, it contains a valid bit. It indicates whether the particular translation is valid or not. And also it contains protection bit. It indicates whether a page could be read from, written to, or executed from. And then there is present bit, and indicating whether this page is in physical memory or not. And also there's dirty bit, and it indicates whether a page has been modified so it's brought into memory or not. And there is also reference bit. It indicates that a page has been accessed or not. So this is sample page table entry format for x86. So this is defined by hardware. So in x86 page table entry, there are 20 bit. So of course this is for 32-bit x86. So page frame number occupies the 20-bit. And there are 9 bits allocated for a flag. So there are prison bit and read-write protection bit, and there is supervised bit, and there is also a bit that indicates that whether this page has been accessed or not. And then there is dirty bit, and then there's page frame number. Okay, what you could see is there are 3 bits unallocated. This is 3-bit. x86 page table entry leaves 3-bit for OS. So whatever the OS is, this can be an Linux or Windows or Macintosh, whatever. These 3 bits can be utilized by the operating system. The rest of the bits in 32-bit entry is used by hardware. But paging is very slow. The reason is why. Paging is to translate the virtual page number to the physical frame number. But to do the translation, it has to access memory and read the page table entry from the memory. So the objective of doing translation is to access memory in some cases. But to access memory, it has to read the page table, and to read the page table, it has to access the memory. So every time the operating system needs to execute an instruction, there comes extra memory access for the page table. So to find the location of the desired page table needed So every memory reference paging requires the OS to perform one extra memory reference. Let's look at this sample code. This is a software representation of accessing memory with paging. Of course, this can be implemented in hardware. First, from the virtual address space, it extracts virtual page number. And then out of using the virtual page number, use it as an index to the entry in the page table, and then starting from the page table based register, and then add the index of the page table, and it'll get the address of the page table entry. And then it reads the contents in the page table entry address, and then it gets the actual page table entry. After it obtains page table entry, it checks whether a given page table entry is valid or not. And then after finding that the valid page table entry is valid, it checks if it has proper permission or not. If this test passes, then it obtains the offset of the page, and then adds the offset to the page table frame number to get the correct physical address. And then using the physical address, it reads the memory and then sets it to the register. Let's look at the example of how page table entry and address translation affects the overall program execution. This is a simple program. There is an array of 1,000 integer, and there is a for loop, and in the for loop, the program assigns 0 to individual entries. So we compile it, and then as a result of compilation, we get this simple assembly code. First one, it assigns 0 to whatever the address here is. And then it increases the EAX register, which is an index to an array, by 1. And then check if the index is the same as 1,000. If they're not the same, then it jumps to the address 1024. And 1024 is the starting address of the loop. So this program iterates this loop 1,000 times, and each time it iterates the loop, it assigns 0 to whatever address this register represents. This is a memory trace of accessing and executing this 4 lines of assembly code. There is move, increment, compare, and jump not equal. Then it iterates these 4 assembly instructions for 1,000 times. And let's look at the virtual address of individual instruction. This is 10,024, and this is the next instruction, and the instruction after, and the other one. So in virtual address space 10,024, to get the proper physical frame number for this virtual address space, we have to consult the first page of the page table 1. Okay, so first 4 instructions, this one, and this one, and this one, and this one, the 4 instructions. And then in move, move not only an instruction, but in the course of executing instruction, it accesses memory, and it accesses the array of 1,000 instructions. And also assume that those memory are located in the stack, and it's located in 40,000 address space. Okay, and it increases by 1, 2, 3, 4. So the actual physical frame number for 40,000 virtual address is, you can find the corresponding physical table entry by computing, performing a next division of 40,000 divided by 1024. Using this interpretation, we can get the physical address of individual virtual pages. The issue here, it's expensive, because every execution of a memory requires additional memory access for address translation. That is serious overhead in paging.